We're happy to have Sruthi Narayanan from Perimeter tell us about soft charges and energy correlators in the end formalism.
Yeah, thanks for having me. It's been nice to spend some time here. Talk to everybody. Yeah, it's sort of a long title, but hopefully by the end of this, you'll have all of the terminology down. It'll actually make sense. So I'm going to tell you about some upcoming work, hopefully soon, with Ian Molt and Sabrina Postarsky. And please stop me if you have questions. This is the first time that I put all of this together to actually present about it. So if something is confusing, I would very much like to know and I would like to clarify. Okay. So I'm just going to start with an outline. So my goal today is, and I hope that this is what you take away from this presentation, is to relate correlation functions of some familiar operators from flat space holography to what are called energy correlators. So I'll define all of the ingredients to explain that statement, but that's sort of the takeaway from this talk. So I'll start with sort of a motivation from the asymptotic symmetry side and make some comments about flat space celestial holography. And then I will also we'll shift to review some of the relevant things from the energy correlator literature. So this will be like detector operators and how we actually construct observables. And then I won't do out the whole computation for you because it's too many details for a talk. But if you want to know the details of anything, please come and talk to me at some point. But I'll do calculations of the 1 and 2 point functions just to illustrate how these quantities on either side are actually related to each other. And I'll make some comments about gravitational memory and talk about where we can go from here. I should preface by saying that my motivation, broadly speaking, for this project came actually from the gauge theory side and wanting to understand some things about QCD and not actually in the context of gravity. Turns out that's really hard. So especially for someone whose background is primarily in gravity. So my hope is that if we can understand these things in a gravitational context, then that'll give us the ammunition to actually go forth and understand things in QCD and yeah, other related areas. So sorry about the top. I don't have a mouse. It disappears, so I can't press OK. Okay, so I'm going to start with a little bit of a history lesson, at least for some, maybe not all. But okay, this is some old literature on asymptotic symmetry. So I mentioned that sort of half of the motivation for this problem comes from trying to understand some concepts in asymptotic symmetries. So these are the set of symmetries of asymptotically flat spacetimes. Okay, so if we look at this Penrose diagram, I also tried to put pictures to make things visual. Hopefully it's helpful. But the point of this is so that you will remember it. It will appear a lot. So what we do is I'll be working in 4 dimensions here. You don't have to, but for our purposes, 4 dimensions is perfectly fine. So we usually use Bondi coordinates. So they're depicted here on this Penrose diagram. So R is the thing where if you take it to infinity, it takes you to this boundary here, which is future null infinity. There's the boundary in the past here, which is past null infinity. So this is just where all like objects originate and where they end up. U is the coordinate that parameterizes movement along a null infinity. So I go from minus infinity to infinity and I move along this boundary here. Each point on scribe, on null infinity, is labeled by a 2-dimensional sphere. And the 2-dimensional sphere is parameterized by angular variables z and z bar. These are just stereographic coordinates written in terms of your usual 2 angular variables. So if I take these Bondi coordinates and I write out my usual flat space metric, then I'm going to get this red boxed thing here, okay? But what I care about is corrections to this metric, so perturbations to this metric that fall off in some order in 1 over R. And that's all these guys, at least to leading order, that appear beyond that. And what asymptotic symmetries do is they classify groups of these asymptotically flat spacetimes which have the same fall-off conditions. So if I make a transformation associated with a particular asymptotic symmetry, then I'm preserving the fall-offs of my perturbed metric components. So some of the relevant quantities here, at least the primary quantity that will be relevant for us, is this CZZ tensor. This is the shear, and it's what describes gravitational radiation in your space-time. And that's going to be a fundamental object that we work with when I actually show you equations for things beyond just a metric. Okay, so keep this Penrose diagram in your mind. Will come in handy. Okay, but from this, again, more history, from this understanding of asymptotic symmetries, it was realized that there's actually three related physical phenomena. So on one corner, so this is the infrared triangle, for those of you who have heard about it. On one corner, you have asymptotic symmetries, which I just talked about. But if you construct the charges associated with these symmetries and then look at their associated word identities, you find that they're actually related to something that's more familiar in the context of scattering amplitudes, known as soft theorems. And so that sort of gives a very nice relationship between the symmetries of these sorts of spacetimes and the scattering that you might observe that happens in the bulk. And the third point is what are called memory effects, which are, when I'm talking about a soft theorem, I'm talking about some particle that is taken to be energetically soft. So that corresponds to, in the Penrose diagram that I showed before, some sort of radiation that's coming out at null infinity. And all that radiation is going to have an effect on asymptotic observables. And the effect that it has on observable quantities is what is known as a memory effect. And I was trying to figure out, so I actually don't have a slide dedicated to celestial holography in this talk because I don't actually do much with it per se. But I should also mention here that one of the nice things that came out of this whole story is that if I look at asymptotically flat spacetime, I can recast scattering amplitudes in the bulk spacetime as conformal correlators on the boundary. And so there's actually a holographic two-dimensional CFT that lives on the boundary, and that gives you sort of an additional toolbox to be able to try to calculate some things that are maybe a little bit more obscure in the usual context. So that's also spun off from all of this. I'm not going to talk about it in a lot of detail here. I'll allude to it a little bit at the very end of my talk. But one can construct operators in the CFT that correspond to like these soft theorems, et cetera, et cetera. Okay, so there's a set of asymptotic symmetries associated with asymptotically flat gravity. In this talk, I'm going to concentrate on the leading order guy, which is super translations. So I'm just going to review for you some of the basics of super translations. So this is the one that's going to preserve the leading order fall-offs of my asymptotically flat metric. So if I look at my Penrose diagram again, then I can understand super translations of like translations along scribe. So if I write it in terms of a killing vector C mu, I see that, okay, I'm simplifying things, there are other terms here, but it basically looks like some function of z and z bar times partial u. So from the point of view of the IR triangle that I drew before, if you take super translations and you write out their word identity, then you're going to find that that's actually equivalent to the leading soft graviton theorem. And then if I actually look at the passage of the effect of the passage of that gravitational radiation on observables that you calculate at the boundary, then I see that you actually get the gravitational memory effect. So those are the three corners that we will be concerned about in this talk. But I should emphasize that even though we are focusing on super translations, conceptually, it seems like there should be an analogous construction for, say, super rotations, which is the subleading symmetry, and presumably for more subleading symmetries. But it becomes technically more difficult just because the the actual transformations are a little tricky. The connection to detector operators, which I will talk about in a minute, becomes a little tricky. But in principle, I think there should be equivalent relationships, and I will also comment on that at the end. Okay, so now I have to show you some math. This doesn't have a picture. Most of my slides have pictures, but not this one. So as I said, for if you have a symmetry, then I can construct a charge. So we usually write down this charge as Q plus and Q minus. So this is just the charge that acts on the out states, and Q minus is the charge that acts on the in states. So this thing that you see in the middle here is basically the commutator of Q with the S matrix. So this thing being 0 is the statement of the word identity. And then what I do is I write out Q plus and Q minus. I didn't write it here, but it has an analogous form in terms of in this equation up here, you can write it in terms of an integral of this function f that parameterizes the super translations, and this parameter mb that appeared in the metric at leading order, which is the Bondi mass. But it's actually more elucidating to use Einstein's equations to rewrite this charge. So you use this equation for the Bondi mass here and plug that back in, because this term here, so this NZZ, is related to the CZZ that I described earlier, the shear tensor. So this is called the news, and it's just the derivative of the shear with respect to u. And then TUU here is the matter stress tensor. This 2 superscript here just means that I have extracted the order 1 over r square part, because that's the one that contributes to this Einstein's equation. Now when I plug that back in to Q plus, then I see that it separates into several terms, but I'm going to separate it into 2. So this first term here has all of the information about the radiative modes, and this one here has the stress tensor, so the matter information. And why is it, so we call this first part the soft charge, and we call the second part the hard charge. Why is it nice to separate the charge into 2 pieces? Well, if I do so, then I see that if I, so I didn't, sorry, I actually meant to write that out, I'm sorry, but CZZ, I said is, describes the gravitational radiation, right? So I can write it out in a mode expansion in terms of creation and annihilation operators. And if I do that and then I write NZZ, what I find is that the soft charge can be realized as basically the insertion of a soft graviton. And the second part, which contains the matter stress tensor, is basically measuring the effect of that insertion on all of the hard matter in whatever scattering process you're talking about. So that's minimally depicted in this picture in the corner here. So this red blob with sticks coming out of it is supposed to represent whatever scattering process I have. And in particular, I can add some kind of a soft leg to the scattering process. That would be the insertion of this guy, and then the effect of that on all of these other hard legs is going to be measured by this.
There's no F dependence in the multiple.
Sorry?
The F dependence constant in the multiple.
The F dependence?
Yes.
So
Yes, there
Yeah.
is.
there's
It's just a misprint.
sorry, there should be an F there.
Okay,
I just forgot to write it. My mistake. It's just a typo.
And the matter is assumed to be all massless here.
It doesn't have to be, but for our context, I mean, it can be whatever matter.
There are massless particles. There is a separate contribution from
Yeah,
And
there's gonna be a separate contribution, so for our purposes, everything is massless.
Okay.
Yeah. Right, sorry about the F. Okay, that might track through, I apologize for that. So now if I write down NCZ in terms of A's and A daggers, and then plug this guy into the word identity that I had before, I can show that the soft part of the word identity is basically the left-hand side of this equation here, which is just the insertion of the soft graviton. And the right-hand side gives me the soft factor, because that's just the action on all of the hard matter. So in that way, we can see that the word identity is equivalent to the soft graviton pair. Okay, and I promise all of this is relevant, because what I want you to take from here is I want you to remember this hard charge here, and I want you to remember this Penrose diagram here.
Sorry,
Yeah.
if there are also hard gravitons in the process, where do they?
So okay, if there are hard gravitons, okay, so there's
Can they be in T2? You mean matter means,
yeah, matter just contains everything.
Yeah.
Yeah, but
because, yeah, T contains also parts quadratic in N, which
Correct.
is the hard
So-
graviton.
right, so that's what I was just gonna say. So in the previous, sorry, so maybe I was too fast. So this guy here is actually the sum of these two terms, right? So this NZZ part is the one that would contain information about hard gravitons. So there's the distinction here is whether you do the shear inclusive term or the not shear inclusive term. We assume that in so that's just a distinction in how this second charge is defined, whether or not you have hard gravitons. Okay. Is that clear?
Yeah, I'm just, so soft graviton here, it just means normal graviton with small moment, soft momentum.
Yeah,
and
okay, so you're taking it energetically soft.
But I guess my confusion, what the scale which sets separation between what you include in this quadratic part, which you call hard graviton, and what you
You mean, how do I define the soft
right,
scale?
right,
Um,
and where it enters in all the world.
yeah, so in principle, I have to define some cutoff here where, like, you know, I have so that I can actually define some notion of soft.
I suppose that, I mean, in the limit here, you integrate over sky plus, right? So
Right.
it's strictly infinite wavelength, right? It's the soft.
Yeah.
But
this
the other
is-
one wants to make a statement about actual gravitons with small momentum.
There's something I never understood. Right? I mean, that what is, because in all the papers on this story, this soft place to roll, it's either really omega equal to 0, or is an approximation of omega much smaller than the characteristic scales of a physical process. And I never saw this done properly. I mean, you know, when you study the infrared divergences and you look at Weinberg, then there really you can see lambda 1, lambda 2, lambda 3, and you can really put numbers. In this story, I never see how numbers are put. I mean, not even in my paper.
But maybe in your place, correct?
No.
The strictly zero energy gravitons are moving in some direction, so they actually do carry some sense of angular momentum. So that's like one way you can approach them.
But you should, okay, yeah. I mean, yeah, we can. Yeah, okay, maybe we can talk about it later. I don't have a good answer to.
I think it appeared in some papers that Prahar Mitra wrote, where they like clarify this issue of like where you put the cutoff and then where the soft vector is and like what the right order of limits is that you take in more recent papers. on in abelian gauge theory.
Okay. Okay.
But
Yeah.
I don't. Those.
Uh,
I suppose that this may become clearer when you talk about the memory effect.
well, my discussion of the memory effect is gonna be at the very, very end of the talk. So. I don't think so, but because it's gonna be more of a heuristic discussion at that point, but yeah. Okay, so. Okay, so we've established the word identity and hopefully convinced ourselves that there's two terms that contribute to the total charge. And so for the moment, what I want to do is I want to just pivot to talking about the second part of the motivation for this project, which comes from detector operators and energy correlators. So, oh, sorry. Okay, so what you should see instantly before I say anything is that we have a diagram here that looks very much like the Penrose diagram on the previous slide. And we have a definition here that looks very much like the hard charge that I wrote down. Okay, so that's why you had to keep those two things in your mind. So recently, there's been a lot of interest in trying to understand what are called energy correlators. So in order to actually define what those things are, we need to go back to the building blocks for those objects, which come from the seminal paper by Hoffman and Maldacena, which you should definitely look at if you're interested in all the details. And what they do is define a specific class of light ray operators. And light ray operators are objects that are integrated, that are integrals over scry here, right? So these black lines that you see here are like the locations of these guys. And in particular, they concern themselves with one type, which is called the energy flux operator or the average null energy operator, ANIC. And this guy, so n here is some unit vector in 3 dimensions. Okay, this should be a d equals 4. Their construction is an arbitrary dimension. So this guy parameterizes some point, some angular point. This t here is a specific component of the stress tensor. And so if you decide to take this guy and write it out in the bonding coordinates that we're more used to, what you'll find is actually that this thing looks basically the same as the hard charge that we wrote down on the previous slide. You can also
For clear that.
so in this, good, thank you. In the case where you set f to be a delta function, yeah, we set f to be a delta function. So which is what we will do moving forward. One can also define an analogous charge flux operator, where instead of the stress tensor, you integrate some like global U1 current or some other spin 1 thing. But for my purposes, I won't be talking about the charge flux. I'll concentrate only on the energy flux. So what does this actually do? If we turn ourselves to this diagram here, we see that this looks very similar to what we had before because, okay, I have some scattering process here, right? And they were fancy. They, did things in terms of actual like things that look like particles. So, I have some collision that happens here and then stuff comes out, maybe it's jets, maybe it's, we don't know, whatever. It's a bunch of stuff. And then it hits somewhere on future null infinity. And these energy flux operators, the goal is to say, okay, I place them at various points at null infinity, and they kind of act as like calorimeters. So whatever comes through, it measures the energy flux that comes through that point. And I can talk about, what is the correlation function between these guys, which measures, what is the correlation between the energy that's output here and the energy that's output there, because they're defined in terms of angular positions on the boundary. And the notion of so that sort of lends itself to, well, can you do this? Can you actually do something with this in experiments? Because we're talking actually about measuring some sort of energy flux that's at asymptotically far distances from wherever my collision happened. So that requires an actual calculation of some object that you might be able to realize.
Wait, here, was it important that there's like minus infinity to infinity and the other one's 0 infinity? Did it matter?
There was zero to infinity.
It's on the definition, so you don't have to propose. Definitely.
That's a good question because I took them from the same paper. It should be 0 to infinity for both, yeah.
But does it matter that the limit is inside or outside the integral? So in the first definition, you take the limit first and then you integrate. And in the second, you do the opposite, right? You integrate and then take the.
So okay, both, sorry, I think maybe. Okay. I have to check the paper that I got these from, but there shouldn't be a difference between the definition of the energy flux and the charge flux operator. So there shouldn't be any difference in the limits that you take. And I think usually the way that you write it is the second way. So even for the anic operator, you write the limit with the power of r out front and outside of the integral. You don't put it inside the integral. Okay, so in order to actually try to relate this to something more realizable, we need to calculate something that is actually potentially observable. Oops. Okay, so that's where we get what are called energy correlators. So in the original paper by Hoffman and Maldacena, they assumed that the theory they were in was a CFT. So they had some kind of bulk CFT. They were talking about scattering in the CFT, and so in that case, when they wanted to compute what these what the endpoint functions of these anic operators were, they were able to use CFT techniques and actually write it out in terms of a correlation function of components of the stress tensor, because that's constrained in a CFT. We know what that form looks like, and we're able to compute, 1-point functions, 2-point functions, etc. But one doesn't necessarily always have a CFT. So that is one big question that I'm going to put aside for the moment. But you might be in you might be in a situation where a CFT is a good approximation for the regime of whatever theory you're trying to probe. And in that context, the endpoint functions and also the operator product expansions of these operators have been able to connect to experiment in several ways. So I'm not an expert in this by all means, but if you are interested in the details of all of these connections, this paper here is a great review from earlier this year. But just a few that I think are particularly interesting. They've been able to relate it to measurements of jet substructure. So this is like actually writing out weighted cross sections, which you can write out in terms of these energy correlators, which is also related to jet shape observables and determination of parton distribution functions. So basically, they're able to probe the structure of jets and probe the structure of other hadronic observables. And they have actual data from the LHC where they say, here's what we've computed theoretically, and here's how it agrees with what we're able to see. So these are real things, which is what excites me. But I would like to, given the similarity between this anic operator that we write down here and the hard charge that I talked about earlier, it would be really nice from from the perspective of making more future experimental connections, to relate what they have done to what has been done from the asymptotic symmetry side of things. But a lot of what we talk about in the context of, you know, soft theorems and that sort of thing is in the context of scattering amplitudes. We're always talking about, you know, we have an S matrix and, you know, we calculate some amplitude and that's what we work with most of the time. So the question is whether, you know, outside of the CFT techniques that were used originally, can you calculate these quantities like energy correlators in the context of scattering amplitudes? And the answer is yes. So in a paper from 2023, they introduced a different kind of asymptotic observable called momentum space radiation waveforms. Okay, it's a fancy name. We're going to call them in correlators because that just, I don't know, sounds easier to parse in calculation form. But the aim was to answer the following question: what is the expectation value of some field after some collision has occurred? Okay, so instead of saying that, so if we look at this side, right, this is the usual way in which we think about some kind of S matrix observable. You say that, okay, I have a bunch of stuff that comes in, I have some interactions that happen, things collide, things interact, and then they come out. And based on what I measure between the overlap between the out state and the in state, I'm able to tell you about the interactions that happen. But this is asking a different story, a different question, which is, suppose a bunch of collisions happen. How does that affect the measurement of something else? Like, for example, how does that affect the measurement of the electromagnetic field? And so for that, what you're actually doing is computing something like this, where instead of having an out state, you have another in state. And you take the limit where this in state is the same as this in state, and the observable that you're actually that you actually care about lives on this cut in the middle here. So the thing that you're actually calculating is, you know, some operator that you insert at this cut. And the way that we should understand this is, I have a picture on the next slide, which will hopefully visualize that in space-time. But I take, for example, this thing up here where both sides of this are understood to be an in state, and I sandwich a complete set of out states in the middle, so that then I get objects that I realize as, you know, something that looks like a normal S matrix element. Except that now what I have to do is I have to sum over all of these things, right? So, you know, I'd say that I have some box space and I have to sum over, you know, 1 particle plus 2 particle, 3 particle, all of them, right? And that gives rise to another type of complexity. So what you say is usually, at least at this point, what's been done is to say, well, we computed at, you know, leading order in that expansion. And you say, okay, I just do things where the out state is a 1 particle state, or just do things where it's a 2 particle state. But what it does is allow you to actually calculate this observable quantity.
Wait, for that to be an observable, do we want the entire operator to be Hermitian? So like 6 has to be 1, 2 has to be 5.
Yes. Yeah, so that's why you want you want to take the limit where the in state and the out state are the same.
Good.
Right? Yeah.
Okay, so these
Yeah.
are,
Yeah. This is just like a heuristic. Yeah. Okay, so this is not really what's happening. This is just how it's easier for me to visualize how these two things are related. So in this first picture, this is our usual S matrix calculation, right? We have some things that are here at past null infinity. They come in, they scatter, they go out future null infinity, right? And that's how it looks like in space-time. Okay, but here what I'm doing is essentially I can think of it as like this is one scattering process like that. This is another scattering process like that. And then I'm like gluing them at this boundary, and that's the equivalent of summing over these out states. And so this is why it kind of makes sense if you think about, you know, the relationship between this diagram and this diagram, why what you might get is something that can be understood in terms of an actual scattering amplitude. Because, you know, I have a scattering amplitude here, and then I have an S matrix element here, and then I have its conjugate on the other side. So what we will concentrate on is these in observables. And if you go to the Hoffman-Maldacena paper also, you will find that in their construction of these correlation functions, they also did the same thing. So the two states that they sandwiched on either side were the same state. So they weren't, you know, so this is just a way to sort of formalize that with, you know, all of the rules about how your creation and annihilation operators work, how the S matrix plays into it, and et cetera, et cetera. So my point is, we're not doing anything different from what was done originally. It's just,
Here was they were able to explore positivity of this operator.
sorry.
So there they were able to explore
Positivity.
of this operator by considering the same type configuration.
Yeah.
Were you be able to say something similar?
We have not. I think there is a discussion of about this in the paper that in this one here. Of course, they're not working with ANIC operators in that paper, but they also talk about the implications for positivity of whatever operator you insert in the middle. But for our purposes, we didn't explore that.
But isn't the positivity statements made in the original paper, it has to do with it, it's like an ANIC operator, so
Yeah.
the generic operator. Why do you even expect positions? Or not an inner, like not.
Not an ANIC
It
operator.
was a charge operator, why would you even expect?
You might not expect positivity.
Positions?
Yeah, I guess, sorry. So I guess by considering the ANIC. I would have to go back and see, because I'm not actually sure whether it's an assumption that we're making that about the positivity of the ANIC by just saying that it is an ANIC operator. I haven't checked those assumptions myself, so I'm not sure. Yeah, it might be implicit.
Positivity of ANIC is only proven in CFT. Maybe
Is it
the
only
topic
proven in
proof,
CFT?
maybe the topic proof can be generalized too.
But you might expect, like you could,
Yeah,
it's an
yeah,
assumption,
it's
to like
reasonable.
energy and just with charge. It's like-
There's nothing safety.
No, that's what I was saying.
Yeah.
Maybe it's expanded in entropy.
In safety, we have more positivity conditions, like the old family, J family.
Yeah.
Okay, so. Right. So the question now is, given that we have this in formalism, how do we actually compute something, right? So as I said, these operators should be understood as detectors that measure the energy flux at a certain point. And if you go look in this paper down here, you'll have the definition for you know, how you can actually, like, what are the Feynman diagrammatics and all that sort of stuff. But the upshot is that you can basically say that it's the insertion of a vertex factor V. So consider this diagram here. I say that I have, you know, my in state consists of some n particles, and what I'm just looking at the contribution to the in correlator when I have only a single particle state that I'm you know, as I said, you can sum over all of them, but I'm just looking at the leading order term. And inserting a detector here just means that I'm inserting this vertex operator V, which is basically going to measure the flux that comes through this point. And V is given in terms of like an integral over some parameter beta, which, okay, so you have to do the whole thing, but if you parameterize it in terms of the coordinates that we're more used to on the two-dimensional celestial sphere, boundary sphere, it basically just ends up looking like this delta function, where W1 and W2 are the angular coordinates associated with momenta P1 and P2. And that fact that it reduces to a delta function is probably the most crucial point to realizing why these two things are related, because they, as we mentioned, the charge that we wrote down, you had to pick a specific function. You needed the F associated with super translations to be a delta function, and that's precisely why you get agreement between, or we will see that you get agreement between the hard charge and these Anik operators. So if I just to have the expressions here so you can see what they look like, if I insert only one, so this diagram here, it essentially evaluates to something that looks like this. So I integrate over my momentum, this Q in the middle here. I have this delta function, which is what comes from this integral here. And then this part here is the whole reason why we did this, right? Is to relate it to actually some kind of amplitude. So we see that this is just directly related to the square of the n-to-1 amplitude in this case. And of course, there's a momentum conserving delta function which comes along for the ride, where this big P is just the sum of P1 up to Pn. And so this was sort of the point of this paper that I cited here, was to say that in this was specifically in the context of gravity. In gravity, we can write out these 1-point functions and 2-point functions in terms of squared amplitudes, which gives us sort of a nice realization of what these guys are. I also have the 2-point function, which the nicest one to compute is where I have two guys here. Okay, it just looks like you multiplied things together. It's not very elucidating, but okay, so you can compute it. The last thing to mention is that if I decided to consider higher contributions to these diagrams, so for example, in the case where in the case of a single detector, if instead of one particle in the middle here, I had two, right? What that would amount to is, you know, a second momentum that I have to integrate over, and it basically gives you like this. It basically amounts to doing a loop integral. And so the more lines I have here that don't have detectors associated to them, the more loop integrals I have to do. And so just like in regular quantum field theory, where the more loops you have, the harder the computation becomes, that's the same thing that happens here. So as of now, I think there are computations in this paper where they have gone to like 2 loops in the middle. But they haven't really gone beyond that, just because it gets, and the answers become pretty complex anyway. But for our purposes, it's enough to just consider these two diagrams. Okay, so this is right. So this is from the side of actually doing the computation at the Anik, but how do we now relate this to this whole soft charge story, asymptotic symmetries, the super translations that I started with? Okay, so I mentioned that if I take the super translation charge, right, I can write out the word identity. So just to remind you of what the word identity looks like, I have this statement up here, where I have some Q plus and Q minus, and I take the commutator of the S matrix and it's 0. But in order to actually, the first thing you have to do to make a relationship between what we usually talk about as the word identity and how to talk about it in this informalism is you have to make sure you're talking about the creation and annihilation operators the right way. So recognizing that you have A and B, which are basically what you write your in state and out state in terms of, right? They're related to each other by conjugation by the S matrix. That's nothing new. Then, you know, if you just conjugate one of these terms, you realize that writing this as the word identity is the same as writing this as the word identity. Okay, so basically all we've done is taken off the dependence on the S matrix, but kind of sandwiched it all into the fact that now Q plus is written in terms of B. Okay. And the reason to do this is because if you were to keep everything written in terms of the S matrix explicitly, plugging that into an in correlator gets kind of confusing because you have to figure out, okay, like, does this S matrix act on this in state? And so it's much easier to do it where you don't have that at all. Okay, so now we can plug that into something like this. And as I said, you do. So a lot of these computations are just plugging in a complete set of outstates kind of conveniently. So this one wasn't very hard to realize. If you plug it in here, well, this guy now looks like your usual word identity, which you know to be true. So therefore, the word identity is satisfied. Okay, but that shouldn't be very surprising because why would you expect the word identity is no longer satisfied just because we decided to write it out differently? Right, it's still a symmetry of the system. So it's good that that worked out. The fun part of that of writing it out in informalism is actually if you take Q plus and Q minus and separate it into soft and hard parts. Okay, so I can equivalently write out the word identity as like, you know, the left-hand side of an equation is just the soft parts of the charges and the right-hand side is the hard parts of the charges. And the hard parts you can convince yourself because of their action on, you know, the hard matter of whatever your scattering process is. They basically are diagonalized on your out in states. And so, you know, they give you an eigenvalue, which because we have set that function f to a delta function, essentially just gives you the measurement of the energy of each of your particles in your out state. So if you look though at the other side, which is the soft charges, so the QS plus is going to be written in terms of B, and the QS minus is written in terms of A. Okay, the QS plus written in terms of B is you know the one that we don't know. But this guy, it's not hard to convince yourself that it's actually just 0 because this is written in terms of A, this is written in terms of A, and we take the in prime and the in to be the same state. And if you do that, if I add in an A or an A dagger in the middle, then I'm just going to get 0 because those are two states that have 0 overlap. And that's kind of and so the reason I point this out is because in the normal way of writing out the word identity in the usual formalism, you have sort of a symmetry in the way that the terms add and cancel out. So, you know, you have matching between the way that Q plus acts and Q minus acts. But here, at least in the soft part of the charge, the entire part of the word identity on that side comes exclusively from QS plus. Which, if you think about it enough, is also probably not that surprising, given that you know you don't have an out state in this observable. Okay, so I promise there's not too much more here. Primarily just quoting a couple of results. So, oh sorry, keep pressing the wrong. Okay, so now what I can do is I can actually look at the correlation functions of these soft charges. So looking at what the word identity tells us, right? If I write out the word identity as I did before, I plug in a complete set of out states here. Then again, I've separated, you know, so this is the QS part and that's the QH part. I see that, okay, this guy went to 0 as we just argued. So this left-hand side, if I collapse the outstates, just becomes the 1-point function of QS plus. On the right-hand side, I have two terms. One is going to give me just, you know, the eigenvalue of the hard charge acting on this in state. So I've just written it like this. There's an implicit, you know, in overlap here. And the second term, or sorry, the first term rather, which is from this QH plus B, that one is a little more complicated because QH plus B is not diagonalized on the in states, it's diagonalized on the out states. But there's a sum over out states, which means if I decided to write that out as, you know, QH plus the eigenvalue, then I would have a sum over all of those guys. But actually what's nicer to realize is that that's just the anic 1-point function. So that's the insertion of since this hard charge can be understood as the anic operator, that's just the insertion of a single anic operator in an in correlator. So you get a really nice expression which says that the word identity in the in formalism tells you that the 1-point function of QS plus, you could also call it the 1-point function of the soft charge, is equal to the action of the hard charge on your in state plus or minus your anic 1-point function.
You can also envision a situation where the twin states are different and the soft charge contributes, right?
You can. We considered the particular, well, but if you have the two in states being different, if you have the two in states being different, then I think, don't you mess with the validity of this observable just because, like, in order, yeah, I have to think about that. Well, also because if you have the two in states being different, then for example, this term where I take the hard charge and act on the in state, I'm gonna get an overlap between two unequal states, right? So that one's gonna go to 0. So that might, so if you assume that the two states are different, you might just get that, like, the right-hand side of this equation is not very interesting, but I haven't actually, yeah.
It's also then just not an expectation value.
Right.
Well, I thought that, yeah, maybe it was what they wanted.
Yeah, I mean, again, that's sort of what I meant by saying it might not be a valid observable quantity, but I mean, in principle, one could compute it and see what it is. I just don't know what it is, you know, in the context of like an asymptotic observable.
But like you can take the state to get any combinations. There's a different number of particles. This is the game people play in the couple collider. Fun.
It's the question that you can measure
Yeah.
the basis of
Yeah,
the
that's-
matrix, not just
If you take the in state to be linear
Yeah,
combinations.
so
of
that's an
different-
off-diagonal term that Pepper was talking about would contribute.
Okay. Okay, yeah, I hadn't
Yeah.
considered that, but that could be interesting. Yeah, so likewise, I can put in two insertions of the soft charge. And I can, okay, the computation for that is a little bit longer, so I'm not outlining it here, but you have to use the word identity several times conveniently. And what you see is that the 2-point function of the soft charge can be related to the 2-point function of the anic, as well as the 1-point function of the anic. So this means that I have a nice relationship between correlation functions of the soft components of the charge and these anic observable quantities, which is kind of what we wanted from the get-go, which was some relationship between the objects that we talk about in the context of asymptotic symmetries and their conserved charges, and these energy correlators that are maybe more realizable as an observable quantity. So in the last 5 minutes, I just want to say that okay, as I said, this is still a work in progress. We're still fleshing out this part, but we had introduced this news tensor NZZ, right? NZZ was du CZZ. So if we take the integral of NZZ over all of scry, you understand this as basically measuring the shift in CZZ across scry, which is understood as measurement of memory. And okay, you can compute how a super translation shifts this CZZ, but because the soft charge, it was written in terms of like derivatives of this du and zz, right? Derivatives of CZZ. There should be a relationship between the 2-point function of what you might call as the memory operator or the memory mode. And the soft 2-point function that we computed in terms of annex, which is interesting primarily because in this paper, it was conjectured that that the memory 2-point function should vanish because, which was from looking at OPEs in the celestial CFT context. But it's unclear whether this would, if from our analysis here, if we got a non-zero 2-point function of the memory modes, I'm not sure whether that would be inconsistent, just because, you know, they're talking about things in the usual sense where we have sandwiched between an out and an in state. Whereas in this context, we're talking about a soft 2-point function in the in formalism. So yeah, I hope some point soon we'll have more to comment on the memory connections here. But so the point of what we have so far is that there's a nice relationship between in correlators of soft charges and for super translations and these ANIC 1-point function and 2-point functions. And so in principle, both of these are separate observable quantities in a theory of quantum gravity. So the hope is that, you know, one day when, I don't know, future interferometers can detect things like this, maybe these are 2 avenues to pursue to try to understand, to try to have some quantum gravity observable. So as I said, there should be an analog of this story for super rotations and other subleading memory effects. But that seems a little tricky in how to define the associated ANIC operator. It would be also nice if we could make, just like there are statements about OPEs of these ANIC operators, we have statements about OPEs of soft operators in the celestial CFT, which are related to these soft charges that we defined. So maybe there's a nice understanding of how the OPE data on both sides is related to each other. But going full circle back to where I started, I would really like to understand this all in the context of gauge theory, and in particular in QCD, because that's where they're actually able to, they've already said that these 1 and 2-point functions are realizable in experiments like at the LHC. So it'd be really cool if we could connect that to the asymptotic symmetry story in gauge theory. So yeah, that's where I'd ideally like to go. Thanks.
Question, but the first one, like, if I take a theory without gravity, then you get something equal to 0 in particular. You get 2 identities equal to 0, right?
Yeah.
Are they trivial? Were they known? What do they mean? Like, because they're not integrated, right? They don't look completely trivial.
I mean, if you take a theory that just has absolutely no gravity, then
Can
you
show identity, sorry.
sorry?
Can you show the identity?
Yeah. Sorry. Oh. Was it here? Yeah, so if you take a theory without gravity, I mean, if you wanna talk about asymptotic charges, right? Then or you want to talk about asymptotic symmetries, then you implicitly have gravity in your theory, right?
So you're saying that this, I just want the area of an identity, and then the soft part is some annihilation equation operator of the gravity.
Yeah.
Now I just decouple gravity. So I would take, what does it become of this identity? It looks like a very powerful identity, but it expresses the 2-point energy correlator in terms of 1-point energy correlators.
You decouple gravity.
Or
I would have said that if you
everything just breaks down.
I would have thought that everything in this just vanishes if you completely decouple gravity.
But the individual elements in the right hand side, they don't, right? Because you have other particles who can.
I mean, well, what is QH1 if
Yes.
there's no gravity, right? What is this guy?
You have hard matter, right?
Yeah, but it's understood as like the action of adding in a soft graviton on the hard matter. So if there's no soft graviton, then there's no action on the hard matter. So maybe I'm not understanding your question.
Well, I mean, it's even more confusing now because QH1 is 0 and Q soft is 0, then you're saying that the 2-point energy correlator is 0. So it is the 2-point energy correlator.
I think there's a gravitational factor of the gravitational coupling in the hard charge.
Yes.
So if you decouple gravity, you send the left-hand side to 0 because there's no gravitons, and the right-hand side to 0 because it's proportional to like kappa.
Yeah. Sorry, all of
Well, how does that kill the energy 2-point correlator?
Yeah, but the energy 2-point correlator, does it have a factor of G Newton?
well, it has to have
Because
because
it's
when you put in that operator in the middle, right? So this guy was derived in where the in terms of this V, right? So this this V up here, right? That has an implicit factor of the coupling.
So you're saying that some of
Yeah.
some of this-
So
this
somehow
becomes
all of them
stable
are-
in the
Yeah.
Or you have to take the limit more carefully.
Sounds very powerful, it sounds. It's up to fix the energy, 2-point energy correlator, so that's a point. For QCD, you have in mind that for charge correlators and stuff.
That would be the idea, yeah. But I haven't done any. Yeah, computations to that effect yet.
But then maybe, do you have any comments on Sergey's original question about this like low energy? If we're
like-
doing QCD.
Well, okay. My understanding was that when you define the charge flux operators, you do have to be careful about like having what your energy cutoffs are, because okay, I don't know anything more rigorous than that, just because I haven't actually tried to work with them enough. I would imagine that definition of scale would probably matter more in the QCD context than it would in gravity, but I'm also not convinced in my understanding of how significant a role it plays in this context, so. Yeah, because we kind of just usually say that I take energy to 0 and that's understood as being a lower energy scale than everything else in the process, so, yeah.
there's kind of like at least 4 scales, right? Like there's an IR cutoff.
Yeah.
Then in between that, you have the scale of soft particles, and then there's a demarcation scale. And then so the soft, whatever's soft, there's between the IR cutoff and this demarcation scale between soft and hard. And then everything that's hard lives above that scale. And then whatever limits you take can't violate this ordering of the 4 scales,
Okay,
right?
yeah, I agree with that, it's just not clear to me. When we actually take the limit, how that's being implemented.
Yeah, when you
Like how-
talk about soft theorems, I don't. look
Yeah,
at
as far as I know, we never say like. This is the scale that defines a hard particle or some, it's just. We take a limit as omega goes to 0
Yeah,
and
but
Taylor expand and assume that. Everything is well defined, but I don't, yeah,
this only place that I've seen this show up is when people talk about on-shell soft effective actions,
okay,
not when they write down like just the soft theorems.
okay.
More question? Okay, let's think, should we have